Okay, here we go with the second part of the day 19 video notes. We had already started talking about the foiling and factoring process for standard quadratics, and we spoke a little bit about how foiling is what we do to bring groups together when we multiply binomials together to produce a standard form result. But the factoring portion is when we split our answers apart. We talked about the techniques that we can use for standard trinomials where a is equal to 1, and then also about what happens when a is not equal to 1, in other words, after we check for a greatest common factor. So in this part of the video, I'd like to talk a little bit more about the greatest common factor and another technique that's called factor by grouping. The factor by grouping technique is good for some trinomials, but it's also good for larger polynomials as well. So here we go as a matter of notes. The greatest common factor, which we call GCF for short, of an expression is the common factor of the terms in a polynomial. So the common factor, the number that divides terms in the polynomial, with the largest coefficient and the largest exponent. So it's the largest number and letter combination that can be divided from every term, and sometimes we factor out a negative 1. Sometimes the GCF ends up being a negative 1. In general, we use GCFs to make some polynomials that are large a little bit easier to work with. For example, in this case here, we've got some pretty large values. If we're going to use the factoring method from the last video, it would be tough to do with these three numbers being as large as they are. If we take out a GCF, that might make it a little bit more manageable. So here are some examples of GCF factoring. We always check for GCF first. Now in this case, there are only two terms, so we would call it a binomial, not a trinomial. But amongst these two terms, I notice that both of them can be divided by the number 3. And if I can go larger than that, I would. So at first I thought, well, maybe both of these can be divided by 6 evenly. The first number can be divided by 6, but the second couldn't. So I have to stop at 3. Now not only do they have a 3 that's common to both terms, but we also have an n value that's common to both terms. In both cases, I could divide these terms, these monomials, by an n as well. So what I'm going to show is that the 3n, which is acting as a GCF, has been factored out from both of these terms. And I know that it's been factored out, not divided away or disappeared. I know that it's factored out, so I'm going to move it to the front of a parenthesis grouping. And now I'm just going to show the results after we follow our law of exponents. In the law of exponents, we said we would multiply or divide coefficients with one another, so 6 divided by 3 turns into a 2, and an n squared divided by n to the first power leaves us with a single n. 9 divided by 3 is positive 3, and n divided by n is 1. They effectively cancel each other in this factoring. Now here again, the n value didn't disappear, it was just moved out front, but in factored form we would report our answer this way. We have our GCF that multiplies by the remaining polynomial, and if we were to distribute these back together, it would return back to this format. So this is a good answer in the box. Let's try another. In this case, I'm looking at all three terms, and I'm trying to decide a number that goes into or divides all three of those terms. Now a 2 might work. I think all of these can be divided by 2, and that's a common factor, but I don't think it's the largest common factor. I don't think it's the greatest common factor. Not only can 2 divide all of these, but if we're a little bit careful, we'll notice that 4 divides all of these as well. There is not a variable that can be divided from each, so we're going to leave the x's alone, but 4 is going to act as our GCF. So since each term can be divided by 4, I'd like to show the 4 written out front, and we're going to go ahead and report what's left behind after the 4 is divided from each term separately. So the 4 divided by 4 at the beginning will cancel or factor itself out. We're left with x squared. In the second term, we have 20 divided by 4. which is 5, and x has nothing to divide by. There's no variable cancellation here, so we'll call that 5x. And then finally, negative 56 divided by 4. If you weren't aware using your times tables, you can check with a calculator. That ends up being negative 14. Now my argument is that by using the GCF, we've now changed this original problem, which had some pretty large coefficients, to a GCF that's sitting in front of a much smaller trinomial. And the smaller trinomial that's left behind could possibly be factored further. Now if the question asks for us to factor using a GCF only, we would stop here. This is where we would stop if we were factoring out our GCF only. But if we had to fully factor, sometimes they'll say fully factor or factor completely. If we see that phrase or that instruction, then we need to go a little bit further. So if we go a little bit further, we'll note that this 4 is going to remain where it is, but now I'm looking at a standard trinomial with an a value of 1. So if this is factorable, we'll put x's here in this position. And then I have to decide on two numbers that multiply to make negative 14, then add or subtract to equal 5. And I think two numbers that would do that are 7 and 2. And if I had a positive 7 take away 2, then this would be a fully factored answer to the expression above. So again, stop here if you're being asked to factor by using GCFs only, but you would move on to this solution after a second or third step if you're being asked to factor fully or factor completely. Here's another example. In this case, it looks like the number 5 goes into all three terms. I'm not 100% sure if that's the largest one. We could sit down and list all of our factors out separately. So 25 has a list of factors, and 35 has a list of factors, and 30 has a list of factors. We can list all of them out separately and look for the largest one. If you'd like to take the time to do that, you're certainly welcome to. I think with some practice, a guess and check is the best way to go. So I'm going to guess that 5 is the largest factor. I'm also going to note that there are no variables that are common in all three cases. We have variables in the first two, but not in the third listed. So I think 5 is going to be our greatest common factor. So we'll factor out the 5, and we're left with 5x squared. Factor out another 5 here by dividing. We'll call that negative 7x. And then factor out another 5 at the end by dividing, and we'll call that negative 6. At this point, a quick check lets me know that I think we were successful. A minute ago, 5 was the GCF because there are no more GCFs left behind. There are no common factors left, so we got the greatest common factor on the first try. Now here again, this would be a good answer if we were asked to factor by using the GCF only. And if we were asked to factor completely, we would try to factor this remaining polynomial using one of the techniques from before. I'm not going to do that in this video. We'll talk about that more in class if we need to. Now in this final example, I want to note that there is no numerical GCF and there is no variable GCF that's obvious here, but this leading term being a negative sign, that's going to make it a little bit more difficult to factor if we were to continue farther. So as we said a minute ago, sometimes negative 1 can be used as a common factor as our GCF. So I'm going to pretend like I'm dividing each of these terms by negative 1. And in doing so, a negative x squared divided by negative 1 becomes positive x squared. Let's not forget that that negative 1 is sitting out front now. A negative x divided by a negative 1 becomes positive x, and a positive 20 divided by negative 1 turns into a negative 20. Now I find that particularly helpful because, again, if we're factoring and stopping at the GCF, we're done. This is what I would consider a more manageable problem because the negative 1 has been factored out. But more importantly, if I were to take this a little bit farther and factor this group using our standard trinomial process, we'll see that it's much easier to find two numbers that multiply to make x squared, two numbers that multiply to make negative 20 that also add up to positive 5. I'm sorry, positive 1. Positive 1 here. This factored form is a little bit easier to determine rather than having to find items that will FOIL back together to equal our original trinomial that contains a negative leading coefficient. That can be a bit challenging. So hopefully the GCF process is a little bit more clear with these examples, and I hope you recognize that picking out a GCF is sometimes a matter of guessing and checking, but you can also use a specific method as well. Now, to finish out this video, I want to talk about our final technique for this week, and that's called factor by grouping. And the factor by grouping technique is sometimes used for 4-term polynomials. So some quadratics can be written in 4 terms, but usually this is for a polynomial that has a degree larger than 2. But the 4-term polynomials can be factored when a GCF, using grouping, when a GCF can be found amongst the first 2 terms and then the last 2 terms of the polynomial. So we've got 2 separate factoring steps to go along with here. So this week in our Math Excel, these are the last couple questions on the set that have to do with factor by grouping. So what I like to do is I'll put a little mark or some sort of identifier here to keep my mind focused. I'm looking at just the first 2 terms at a given moment and then the last 2 terms at a given moment. It's almost like we're treating this like a separate problem. So if you want to cover up one of these, that would be okay too. Now if I look at the first 2 terms in this polynomial, I can find a GCF amongst them. It looks like both of these can be divided by 2, and I think that's going to be the largest number that divides both of them. Both of these terms have not only one r, but a second r that they can give up, that they could be factored by. So I think 2r squared is going to act as our GCF. 2r squared is going to be written in front of the remaining 2 terms. Now, as I divide or factor out the 2r squared that was common, let's see what we've got left over. The 4 divided by 2 is 2. The r cubed divided by r squared is just r to the first power. The 6 divided by 2 leaves us with a positive 3, and the r squared divided by r squared, well, those end up canceling out, and we're now fully factored. So that's a pretty good start to the process. Let's do the same thing for the last 2 terms in the group. Now here again we see a negative leading coefficient, so that tells me I want to factor out a -1, but we can actually do a little bit better than that. Both of these can not only be divided by -1, but perhaps -3 would be a better choice. That's a little bit larger than 1. So if I write down my -3, that's becoming our common factor for the last 2 terms, we can indicate what's left. -6 divided by -3 is positive 2. And this r has nothing to divide by, so it stays behind. And then at the end we have a -9 divided by a -3, which turns into a positive 3. And we've now again factored by grouping because we found GCFs amongst the first 2 terms and the last 2 terms of the polynomial. Now sometimes Math Excel will ask you to stop here. They're just worried about your ability to find the GCF of the first group and the second group. But in reality, we can take this a little bit further if the pattern is met, if we still have the criterion met for a factor by grouping. And the next clue that we're going to encounter is this one here. If after finding our GCF, we have a common factor in a binomial form that's left behind, then this common factor acts as a, like I said, common factor amongst these 2 terms. We can factor it out and report our final answer as a pair of binomials. Now all of that is to say this really. If after the first step of factor by grouping we see a matching set inside the parentheses, we're going to retain a single copy of that matching set, 2r plus 3, and we're going to create another factor based on the pieces that are left over, the 2r squared minus 3, and put that in its new factor group. As it turns out, this pair of binomials would indeed FOIL back together to make this this standard form polynomial back here at the beginning. We can take the time to check this in class, but for right now I would suggest that you try this one on your own, the double check. Let's move on to our final example, or final two examples. In the middle case here, I think just like before, we're going to look for a GCF amongst the first group and then a GCF amongst the last group. So instead of using these little square brackets, I might use parentheses to identify the groups, and this works just fine as well. In the first group, if I look at just these two terms, I notice that 2 is the largest number that divides both of those terms, and a z squared can be factored from both terms. In the act of factoring or dividing in this first group, I'll note that the 2z squared comes out front, and the 2's here will divide each other and cancel or reduce to 1. Z cubed divided by z squared is going to reduce to the number z, or the letter z. 8 divided by 2 is 4, and z squared divided by z squared is 1. Those will cancel or factor out one another. So far we're left with a coefficient in front of a binomial. In the second group, I'll note that the GCF here is the number 3. Both of these terms can be divided by 3. So I'll note that a positive 3 is the number that's dividing the terms, and I'm left with a z plus 4. Well, here again we have z plus 4 that's common to both groups. So because of that, we can now report our final answer fully factored. We're going to retain a single copy of the z plus 4, and we're going to report the 2z squared plus 3 as the other binomial factor to this problem. Those came again from the coefficients that were sitting in front of the binomial common factor. Now in the last example, we can use the same technique, but you might also notice that there's something a little bit different about this particular example. If you look carefully here, not only is there a GCF amongst the first two terms, but there's actually a GCF across all 4 of them. And not only is that GCF numeric, but it's also variable as well. So I had quickly mentioned a few minutes ago that one of the first things that we do is check for a GCF. This is one of those cases where it would benefit. Do you notice the number that can divide all 4 of these terms equally? And is it the largest number that divides all 4 of them equally? Well, if you think the number's 3, I would agree with you. All 4 of these terms can be divided by 3. Moreover, all 4 of these terms have an x variable that can be factored out as well. So each of these terms can also be divided by x. And what that leaves behind is a 3x that's going to act as our GCF altogether. We have now a 5x to the 3rd power, a negative 2x squared, a positive 10x, and then lastly a negative 4 left behind in our factor group. Now that's okay as an answer. If we were told just to find the GCF, we could stop there, but I have a feeling we can go just a little bit further. So I'm going to try to ignore this 3x that's acting as a GCF out front for a moment. I'm going to focus on what's left behind in this parenthesis group. So I'm going to treat these 2 as a group and these 2 as another group, and I'll look for a GCF amongst them. In this group, I think the GCF ends up being just x squared. That's the largest variable combination that works for both. And in this group, it looks like there's a GCF of 2. Both of those can be divided by 2. So let's see what's going to be left behind after I factor those out. Now I don't want this 3x and this large set of parentheses to disappear, so I'm going to copy that down, but now I'm going to switch to my blue ink and I'm just going to finish out this problem there. If I had 5x cubed divided by x squared, well, the x squared is going to act as a GCF in front of that group, and I'm left with a 5x after the x squared is divided out. In the second term, I have a negative 2x squared divided by x squared, so that's going to turn into a negative 2. And in our second grouping here, the GCF is a positive 2, so I'll factor it out of the way, and I can report that 5x and minus 2 is left behind in that group. Well, here again we've got a common binomial factor to this unusual looking polynomial. The 3x with the large parentheses is essentially undisturbed at this point, but we do have an x squared plus 2 group left over that's adjacent to the 5x minus 2 group. So in terms of a fully factored polynomial, I think this would be a good result. Now it looks a little bit strange because we have the double parentheses here. There's nothing wrong with that. That's okay. But also in reality, we don't need that double parentheses. We can leave the 3x written right next to the x squared plus 2 and the 5x minus 2 without the extra set of parentheses. Neither one of these solutions are fine, and I believe both would be accepted by MathExcel. Now, there's a lot to the factoring methods that we talked about in this video, but the GCF by itself is pretty straightforward. It's when we get into this factor by grouping that things get to be potentially challenging. And so that's why I only chose 2 of those questions to finish out our MathExcel homework for this week. You will have a work day on Friday to work through these, so that would be a great time to ask for help and clarification as we go through them. Please let me know if you get stuck along the way. Thanks for watching.